All right, this is Mr. Weideman, AP Physics, Lafayette High School. We're going to pick up where we left off last time, talking about Michael Faraday's discovery. And we said we needed to determine how we're going to quantify this change in magnetic field. All right, so we came up with this calculation, right? The magnetic field times the area times the orientation of the loop in the field is going to give us this magnetic flux, this Weber. But we're only halfway there. We've quantified it, but what we really need to do is not just have flux, but we need to have a change in flux. That is what gives us our voltage. That's what gives us our energy to induce a current. So let's look at ways and how are we going to make flux change. Okay, well, they're comprised of three terms here. One is the strength of the field, one is the area of the loop, one is the orientation of the loop. So if we can manipulate any of these three things, then we can create a change in Webers. So I can increase or decrease the magnetic field. That's what we did in our demo when we moved the magnet back and forth. I can change the area of the loop. A little bit more difficult to do, but it's doable. And then I can change the orientation of the loop. And we're going to investigate that a little bit further. But the point being is if I fluctuate any of these variables, I fluctuate the magnetic field. And that's what we need. It's not just a magnetic field that's going to create this voltage and therefore a current. It's going to be the change in this magnetic field. And I'm going to maximize this change by what Michael Faraday said, it's going to take some time to change the field. So if I can decrease the amount of time, right, increase the rate change of the magnetic field, then I am going to induce a voltage and therefore a current. So, Faraday's law is verbally, it is the rate change of magnetic flux that will induce a voltage and therefore a current in a wire loop. Now the number of loops or solenoid is just going to amplify the effect, but this is how we compute it. If we do a unit analysis of all these different variables, we'll see that we will end up with a voltage, an energy term, joules per coulomb. Okay, so we're going to kind of recap, and I'm going to concentrate on this delta Webers term here. Because what we need to do is we need to calculate Webers, and then we need to find a way to make Webers change, and or as important, change quickly. So I can manipulate these things, the field strength, the area, the orientation, and I want to do it quick. Right? That will then maximize this term right here, which will in turn maximize the amount of voltage that I produce. All right, so what we're going to do is we're going to concentrate on changing these variables to maximize this term. And what we're going to do is I'm going to concentrate on theta. If we plot theta, we can see that theta, or change in theta, it has a very steep slope. I can get a big bang for my buck here. By changing theta, I can get a very large fluctuation in that term over a very short amount of change in orientation. So we're going to concentrate on this, and we're going to change the orientation. I'm going to change theta. So if I look at our equation, what we're going to do is we're going to simplify things, and we're going to hold all these variables constant. So when we had this on the previous slide, I'm going to take my magnetic field, and I'm going to take my area, and I'm going to make those constants. All right, so if I do that, then I'm just going to vary theta with time. And delta theta over time, that is angular speed, that's omega. So I can replace this term right here with omega. And now for a situation where I just want to change the orientation of the loop in the field, I can just take the strength of the field, the area of the coil, multiply it by the rotational speed of the coil, and then the number of coils that I have, and that calculates my voltage that I am inducing with Faraday's law. So, the reason we're concentrating on this is changing this orientation is accomplished very easily by spinning the loop in a uniform magnetic field. So we can see that as I change the orientation, let's look at the orientation from 1 to 2. And we can see that the orientation from 1 to 2, there's fewer field lines going through the loop as I change that orientation as theta increases until I get to position 3, and now theta is 90 degrees. My loop is parallel to the field. There is no flux through the loop, so I have no current. But moving from position 1 to 2 to 3, I can make this happen very, very quickly with a large omega. And as the loop moves or continues the rotation, what's going to happen is in position 3, the loop has no flux through it. And then when it gets to position 4, I'm at a maximum flux again. So as I get this rotation, I'm constantly increasing, decreasing, increasing, decreasing, increasing, decreasing the amount of flux that's going through that loop. And that's exactly what we're after. We're after those change. But we know when we played with this in our demonstration that if I changed my flux, if it increased, I got a current in one direction. If it decreased, I got a change in the other direction. Which means as I do this, the current that I induce is going to change directions. It's going to alternate. So by inducing a voltage and therefore a current, by changing this orientation, I'm going to get an alternating current. That current is going to first be induced in one direction during one part of the rotation, and then it's going to be induced in the other direction, in the other part of the rotation. And therefore, we've created alternating current. And as we said at the beginning, this is a big deal. If you think of all the different things that affect our lives that require alternating current, this is how it's done using Faraday's law. Now, we learn for Faraday's law that this is how we produce a voltage and therefore a current. And we have another equally important phenomena that we're going to discuss tomorrow. And these reversals of directions, these are no accidents. This is a phenomenon that was predicted by Russian physicist Lenz, and it's called Lenz's law. And there's a lot of ramifications to this reversing of current and how that it happens. So it's kind of the other part of the induced voltage story. And we will delve into that tomorrow. So, thank you for your time, and we'll see you in class.